This looked like a complicated CFD simulation, but underneath all of this, the computer is following just a few fundamental rules. Think about a tiny piece of fluid. It's moving, it's carrying a mass, it has momentum, and it can also gain or lose energy. So we can ask three incredible important questions. Is the mass being created or destroyed? What makes this fluid accelerate or change direction? And where does its energy go? The first rule is conservation of mass. Mass doesn't just appear or disappear. And here is why the physics gets interesting. If the same amount of fluid has to pass through a smaller area, the fluid has to move faster. But conservation of mass doesn't tell us why the fluid changes its motion. For this, we need momentum. Pressure can push the fluid, viscosity can resist deformation, and forces like gravity can also change its motion. So the momentum equation is essentially telling the computer how forces change the fluid motion. And if temperature or heat transfer matter, we need another conservation law, that is energy. Energy can be transported with the flow, transferred through the fluid, or added and removed through the boundaries. Now put all these three together. Mass tells us how much fluid is moving, momentum tells us how its motion changes, and energy tells us how its energy changes. And CFD solves this governing equation across the entire fluid domain. So that beautiful animation you are looking at isn't the physics itself. It's what happens when a computer solves the physics. But now there is a problem. These equations describe a continuous fluid, and the computer cannot calculate infinitely. So how does CFD turn this equation into a number? To know this, subscribe.